This video shows you how to use Python code to calculate value at risk with the Monte-Carlo method. I'll show you how to do it with the keyboard and keep my use of the mouse to a minimum. Like, subscribe, and buy my books. Links in the description below. Let's get into this phenomenal video. To open Google Chrome, press Windows key, D as in Delta, press Enter. E as in Echo, B as in Bravo, press N, press Enter. Tab over to get to value at risk Monte-Carlo method. And the first thing I'm going to do is import necessary libraries that I need to run this code. So I'll import date time as D as in Delta, T as in Tango, import NumPy as N as in November, P as in Papa, import the pandas data frame as P as in Papa, T as in Delta, import matplotlib decimal pyplot as P as in Papa, L as in Lima, T as in Tango, import scipy decimal stats as S as in Sierra, C as in Charlie, S as in Sierra. Control Enter to run this, and it works. The next set of code has to do with the value at risk Monte-Carlo method itself. I'm going to create a variable called N as in November underscore sims, set that equal to 1,000,000. That's going to be the number of simulations. There's going to be 1,000,000 simulations in this Monte-Carlo method for value at risk. I'm going to create a second variable called R as in Romeo, F as in Foxtrot, R as in Romeo. That's going to be the risk-free rate. I'll set that to about 4% per year. I'll create a third variable called time, set it equal to 1. That means this is 1 day value at risk for 1 trading day. I'll create a variable called vol and set it equal to 0.25. That is the implied volatility of the asset. And then I'll create a final variable in this part of the code called S as in Sierra 0 and set that equal to 1. That means the stock price is $1 per share. Control Enter to run that, and it works. Next, I have to create a variable that will allow me to calculate returns with a geometric Brownian motion. So how am I going to do that? I'll create a variable called G as in Golf, B as in Bravo, M as in Mike, underscore returns, and set that equal to the stock price, raised to the exponent power of D as in Delta plus the product of A as in Alpha and R as in Romeo. D as in Delta is the risk-free rate minus half the variance multiplied by the time step. So it's the 1 trading day over 252 trading days in a year. Hence it's 1 over 252 for the time step. I'll create another variable, A as in Alpha, that's going to be equal to the implied volatility multiplied by the square root of the periodicity of the time step. The time step is, again, just time divided by 252, since there's 252 trading days in a year. And I'm using NumPy to do that. That's why I have the N as in November, P as in Papa, and decimal before the square root function. Then I'll create R, the normal distribution, N as in November, P as in Papa, decimal random, decimal normal, with 3 key arguments, 0, 1, and the number of simulations, and 1. That will allow me to create the distribution. Control Enter, and this works. Now I can show the array of returns with the geometric Brownian motion returns that I just created, and you can see there's an array. These curly brackets are called tuples. They are not mutable. These square brackets are called lists. They are mutable. That was just to show the returns. And then I'll create a variable for different confidence intervals I need. So it's going to be 100% minus the 6 arguments equals the confidence interval. So for example, 0.0 1 represents a 9er decimal 9er confidence interval. 0.1 represents a 9er decimal 9er confidence interval. 1.0 represents a 99% confidence interval. 2.5 represents a 9er7.5 confidence interval. 5.0 represents a 95% confidence interval. And 10 represents a 90% confidence interval. I'll set VaR equal to S is in Sierra, C is in Charlie, S is in Sierra, dot score at percentile, with the arguments 1 less than the geometric Brownian motion returns and the list I just created for the different confidence intervals, and then I can show that by typing VaR. And you can see the array, which is again a list inside of a tuple. Now to create the data frame, I'll create an argument called D as in Delta, F as in Foxtrot, set it equal to P as in Papa, D as in Delta decimal data frame with the following arguments: value at risk, purse, the list I created. In the columns, I want that equal to value at risk. That's how I'm going to label it. Show DF, D as in Delta, F as in Foxtrot, press Control Enter, and it works. You can see the value at risk for one-day trading with these different components. And let's plot that visually so that it's easier to understand. So to do that, type PLT decimal hist. Hist is short for history, with the arguments geometric Brownian motion returns. The density is going to be true, and I'll set the number of bins equal to 100. And then I'm going to have 6 dashed lines of different colors for the different confidence intervals that I specified in the list earlier. And then for the label of the vertical axis, I'll call that frequency. X label will be called gross MOIC, which is multiple of invested capital. If I want to show grid lines, I'll type PLT decimal grid, set that the arguments equal to true and the line width equal to 0.5. Then type P as in Papa, L as in Lima, T as in Tango, decimal show with an empty tuple. Control Enter, and this works. So you can now see the value at risk visually, which is easier than the data that we had shown earlier. The distribution is a bit skewed, but not too much. Remember, this is one-day trading VaR. So if you think of the red line, for example, what that says is we're 99.99% confident that we're not going to lose more than about 5% of our capital with this hypothetical stock in any one trading day. Green line is 9er, so we're 99.9% sure that we will not lose more than about, I don't know, maybe 5%. The red line might be closer to 5.8. And then you have the 99% confidence interval for the blue line, 97.5 for the yellow line, 95 for the light blue line, and then the black line is your 90% confidence interval. So this gives you an idea of what to expect Given the data we input into the model with the implied volatility, we ran 1 million simulations. This is one trading day, and we calculated the returns using the geometric Brownian motion function. So take this knowledge into the marketplace to be a better investor, a better user of Python, and better understand the value at risk of investment portfolios that you're working on. Have a great day. Thank you for watching this video. Please subscribe to my YouTube channel, hit the notification bell, hit the like button, leave a comment below, and please buy my books. The links to those will be in the description of this video.